General solutions of trig equations. So let's start with a sine one. Yeah, so if x was equal to sine theta. Well, first thing we need to know is x positive or is x negative? Because that will dictate which quadrants we're in if we were solving a trig equation. So let's assume x is positive. So I know I could be in the first quadrant. Remember, inverse sine is the angle. So inverse trig represents the angle. So the acute angle would be the inverse sine of x, whatever answer we get. But of course, it could be in the second quadrant. Now in the second quadrant, that acute angle is still the inverse sine of x. That would not be the answer for the obtuse angle. So basically our two solutions for this would be the inverse sine of x or pi minus the inverse sine of x for the second quadrant. Well, that's if it's a positive number. What happens if it's a negative number? Right, if it's a negative number, then I'm in the third quadrant. But the acute angle will no longer be the inverse sine of x. It will now be the inverse sine of negative x. Because remember, we said x is a negative number. So if I went inverse sine of the negative number, the answer they give me would be a negative acute angle, which is not what I want. I want the acute angle to be a positive number. So to find it, I would find the inverse sine of negative x. Because if x is negative, that now creates a positive number, and that will get me an acute angle. So the acute angle is the inverse sine of negative x, or it could be in the fourth quadrant, and again, the acute angle would be the inverse sine of negative x. So the third quadrant, pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. But now I'm going to use the fact that the inverse sine is an odd function. So the inverse sine of negative x I could rewrite as minus the inverse sine of x. And here in the second one would become 2 pi plus the inverse sine of x. So in fact, we've actually ended up with the same answers as when it was positive, if you think about it. Right? Because inverse sine of x was an answer. But if we go round the circle one time, I would now be at 2 pi plus the inverse sine of x. So I've got the same answer. And the other one, of course, well, you can see it's quite obvious. They are the same answer. What this means is I don't actually have to worry about whether x is positive or negative. I can simply say that the answer will be, and there's my general formula, pi k plus negative 1 to the power of k inverse sine of x. Because look what happens. I'll get inverse sine of x. Next answer is pi minus the inverse sine of x. Next answer would be 2 pi plus the inverse sine of x. Next answer would be 3 pi minus the inverse sine of x, when I keep adding the 2 pi on. So that's why I've got the minus 1 to the power of k. It takes into account the alternating of the plus and minus of the inverse sine. K, of course, has to be an integer. Let's look at cosine then. We'll do it the same way. X could, of course, be positive. And if it's positive, then I'm in the first quadrant, and the acute angle would be the inverse cos of x. Or I'd be in the fourth quadrant, and the acute angle inverse cos of x. So my two possibilities, inverse cos of x, or 2 pi minus the inverse cos of x. What if x is negative? Well, then I'm in the second quadrant, or the third quadrant. But again, now I have to do the inverse cos of negative x to make that a positive number, and I'll get an acute angle. So I'll get pi minus the inverse cos of minus x, or pi plus the inverse cos of minus x. But we said the inverse cos of negative x was equal to pi minus the inverse cos of x. Well, look what we get when we substitute that in. We can see straight away the same answers. So again, we don't have to worry about whether x is positive or negative. So for this one, my general solution will be 2 pi k plus or minus. So it's always going to be a multiple of 2 pi k plus or minus, because our first one, inverse cos of x. Then I'd go 2 pi minus the inverse cos of x. But then I'd add 2 pi onto both of those. So I get 2 pi plus the inverse cos of x. 4 pi minus the inverse cos of x. I could add on again. 4 pi plus. So we get multiples of 2k, both plus and minus the inverse cos of x. K again has to be an integer. Well, let's do the third one, the tan ratio. Positive, well, tan, I'm in the first quadrant or the third quadrant. Answer, inverse tan of x or pi plus the inverse tan of x. Okay. If it's negative, I'm in the second quadrant or the fourth quadrant, but again, I'd make the acute angle inverse tan of negative x, so I've got a positive number in there. I'll have pi minus the inverse tan of minus x, or 2 pi minus the inverse tan of minus x, but inverse tan was an odd function, so I can change that to pi plus the inverse tan of x, or 2 pi plus the inverse tan of x. Again, same answers, but look what happens with this one. Inverse tan of x, pi plus the inverse tan of x, 2 pi plus the inverse tan of x. Next one would be 3 pi plus the inverse tan of x, and so on and so on. So my general formula becomes simply multiples of pi plus the inverse tan of x. And again, k is an integer. So they are the three formal general solutions. So if I wanted to solve an equation like this, and they have not specified a domain, and this is where they're saying it implies it in the syllabus. Because clearly, if they don't mention a domain, then you have to come up with a solution that covers every possible answer. General solution. My formal solution would be that. Pi k plus minus 1 to the power of k, inverse sine of root 3 on 2. But we can work out the inverse sine of root 3 on 2. That is pi on 3. That would be my answer. Make sure you specify the condition on k. It's got to be an integer. And then you could generate every possible solution to that equation. That's the formal way of doing it. The informal way of doing it, sine theta equals root 3 on 2. Well, I do it like I normally do. Oh, that's in quadrant 1 or quadrant 2. Therefore, it'll be pi on 3 or 2 pi on 3, but oh, hang on, I could keep going around the circle every 2 pi. So I simply say, oh, plus 2 pi k, where k is an integer. Cos theta is minus 1 on root 2. Well, in that case, I'll use the 2 pi k plus or minus inverse cos for that one. Minus 1 on root 2. Well, here's the interesting thing with this. Inverse cos of minus 1 on root 2 becomes pi minus the inverse cos of 1 on root 2. It certainly does. So we get 2 pi k plus 3 pi on 4. Make sure you specify what k is. If I've done it the quick way, cos theta is minus 1 on root 2. Answer is the same as normal. I know I'm in the second or third quadrant. Again, just add 2 pi k onto each of those solutions. And tan theta, let's do a tan one. So that one was pi k plus inverse tan, and that would be pi on 6. So pi k plus pi on 6, where k is an integer. Or I could simply solve it like normal. Mind you, watch out with this one. You actually only need one solution for this, because the period of tan is pi. So you really only need to find solutions in the first or second quadrant. Well, in this case, there's only going to be an answer in the first quadrant, because when you then generalise it, you will get the third quadrant answer, because you'll add pi on, because that's the period. So that's our answer. Ooh, something like this then. Sine theta equals the sine of 5 pi on 7. And it's really tempting to simply say, well, theta is 5 pi on 7. That is, of course, one possible answer. If I want to generalise it, I'll put it into the formula. Pi k plus minus 1 to the power of k, inverse sine of sine 5 pi on 7. But remember, we've got to be very careful with the inverse sine of sine 5 pi on 7, because the inverse sine function only gives us acute or negative acute answers. So 5 pi on 7 would be in the second quadrant, which is a positive answer. Therefore, I'm looking for the positive acute angle. The equivalent acute angle for that one is 2 pi on 7? Yeah, 2 pi on 7. So we get minus 1 to the power of k times 2 pi on 7 for that one. Cos 2x is cos pi on 9. Again, tempting to simply say, oh, 2x is pi on 9. Yeah, sure, one answer. Put it into the formula. 2x equals 2 pi k plus or minus the inverse cos of the cos of pi on 9. Well, pi on 9 is acute anyway, so we do know that's going to cancel. So I get 2x is 2 pi k plus or minus pi on 9. But that's 2x, we want 1x. So x is pi k plus or minus pi on 8. But of course I've got to write down my condition on k. K is an integer. This one, cos 4x is equal to cos of x. This is a bit more interesting. You would think the answer is x equals 0. 4x has got to equal x. X must be 0. But there are, of course, other answers. There's the general solution. 4x is equal to 2 pi k plus or minus the inverse cos of cos x, where k is an integer. Problem is, when I cancel inverse cos of cos x, the answer is not necessarily going to be x. Because if x is positive, it will be. So I would get 4x equals 2 pi k plus or minus x, which tells me, I mean, theoretically I've moved it over and I get minus plus instead of plus or minus. It doesn't really matter, you've still got both options there. So either 3x is 2 pi k, so x is 2 pi k on 3, or 5x is 2 pi k, x is 2 pi k on 5. Well, that's if x is positive. Now, here's the bit. Cosine is an even function. So I know that the cosine of x is equal to the cosine of negative x. Therefore, the inverse cos of cos x must be the same as the inverse cos of cos negative x. Must give me the same answer because cos x is the same as cos negative x, cos being an even function. So what that means is, when I get this negative, and again I've got 4x equals 2 pi k plus or minus x, I don't actually have to consider that case. It has to give me the same answers because cos of x is the same as cos of negative x. So I actually don't have to worry about the plus or minus. What that basically means is there's my solution. 2 pi k on 3 or 2 pi k on 5 where k is an integer. Try a sine one. So sine of 4x is equal to sine of x. There's my general solution. But that's for 4x, of course. Again, we have this situation of inverse sine of sine x. And we'll get different answers depending on whether x is positive or x is negative. So let's see what happens with this one. If x is positive, well then I will get just x. So 4x is equal to pi k plus minus 1 to the power of kx. We now have an additional problem. Whether k is an odd number or an even number will determine whether that is plus or minus. So if it is an odd number, then I'll get 4x is pi k minus x, which gives me the solution, x is equal to pi k on 5. But remember, that was only if k is an odd number. Well, instead of writing it as k is an odd number, I've said, well, let's write it this way, times 2n plus 1 on 5, where n is an integer, because if I sub an integer into 2n plus 1, then I'm guaranteed to get an odd number. There's my solution. What happens if it's even? Well, if it was even, then this would become plus x, so 3x will now equal pi k. But now k is an even number, so I'm going to say it's 2 pi n, because 2n will guarantee an even number. Remember, that was just if it's positive. What if it's negative? So inverse sine of sine x will equal x. That's the equation we're trying to solve. But that's the same results as when x is greater than 0. What? So in other words, we do. What I guess I'm getting at is I don't have to worry. Where I do have to worry about odd and even. Yeah. So we end up with these two. Now, oops, before I go there. Look, I think I've taken that way and beyond what the new syllabus is suggesting. I really think that the only thing they're saying is, if it doesn't have a domain, we're recognising that you could have 2 pi multiples plus the actual answers. The general solutions themselves certainly can be useful in solving them, but I really don't think we're going to get ones like these last couple that I did.